Okay, I'm going to present my presentation. So the topic which I'm going to present in this conference proceeding is computational fluid dynamics modeling of the spray process of resin over a laid up fiber stack for the purpose of fiber impregnation in composite materials manufacturing. Actually, this is a PhD, part of a PhD research work. Which is undergoing with collaboration of Bahir University with Kelwan University, that is presented on the slide. And I'm a PhD candidate, and my name is Amare. So I'm going to present the details of this paper. So when I come to the outline, which I'm going to present, it has 4 topics: the introduction, the material and methods, results and discussion, and finally there will be a conclusion and a recommendation. Okay, so when I come to the introduction, it's about composite materials. Composite materials are a combination of materials which has more than one type. So always when we are talking about composite materials, we are saying combination is minimum of 2 materials. So the intention of this composite materials is actually getting a specific property which we cannot get from pure materials. These are actually related when compared to other material types such as pure metals and alloys. These are relatively newer version of engineering materials. Among the different types of composite materials, fiber reinforced plastics are highly applicable composite material groups. These fiber reinforced plastics, as the name indicates, there is reinforcing fiber. Actually, these fibers may be glass fibers or carbon fibers or Kevlar fibers. Actually, this glass fiber is a ceramic type of fiber, and this carbon fiber, as the name indicates, it's a carbon fiber. And also there are natural fibers like bamboo, which is now in an active research area. And as a binder, this ceramics or fibers are combined with resin binder. Actually, this resin binder, the other name of this resin binder is matrix. There are polyester matrices, epoxy matrices, vinyl ester matrices. These are commonly practiced thermosetting plastic groups, but there are also some researches on natural matrices. So combining these materials of different nature or different characteristics is not as easy as manufacturing pure metals or plastics, because here we are not working with a single product, rather we are working with combining products, materials of different nature. So the practice is relatively difficult as compared with manufacturing pure metals. So what are the current available manufacturing techniques for these fiber reinforced plastics? When you see that hand lab, it is about 22% of the practice in the world is hand lab. That's a primitive type of the process, or related open mold processes like spray, chopped spray process. And also there are closed mold processes like resin transfer molding, injection molding, compression molding. Actually, this injection and compression molding are the plastic manufacturing versions. We are using this injection and compression molding for pure plastic manufacturing. These methods come with some modification to these composite materials. And also we have autoclave, continuous and other continuous processes like pultrusion, which will produce a product, continuous production. And also there are other modified processes. So there are a lot of varieties available, and still the area is in current research because people want to manufacture as fast as plastic or metal. And when it comes to plastics, currently we can manufacture a product within a few seconds, but it's not possible for composite materials with the current stage. So it is an active research to bring as fast as possible or higher productivity. There is an ongoing research process which I'm working for my PhD. This is a kind of setup, process setup, which incorporates spraying and compaction. That means there will be a mat, or there will be some textile of fiber, and there will be also the thermosetting matrix, or the unsaturated polyester resin will be sprayed over the fiber, and after the spray it will be compacted, or it will be pushed against the mold, so that it will be infiltrated with the liquid or the thermosetting plastic. This is the general setup. It's possible to see here the general setup for the process, as you may observe here. Here is the setup. These are, we can call it the mold setup. And if you see here, this is the red one. This is a plate, and under this plate there is a lead fiber. The fiber is laid over here. Actually, this plate is a kind of moving in and out. If you see it, it can be move out on this one, and it can be entered through this one. So first, the fiber will be laid against this vertical wall or mold, and we're going to spray the resin by just fixing the nozzle tip here. So when this door is closed, it will have a perpendicular position for the laid up fiber, so the resin will be sprayed. Then after the resin is sprayed, immediately this plate will come down, and this balloon will be expanded so that it pushes the sprayed resin against the vertical mold, so that in the middle, that means in a sandwich position between this red plate and the back mold, the sprayed resin will be infiltrated against the thickness of the laid fiber. Actually, the fiber may have 3, 4, 5, 6 layers of clothes of fiber, depending on the requirement. So this is the general setup. But in this general setup, or in this general research work, and for this paper, I'm going to present the spray parts. Even in the spray part, it is about the selection of better nozzle for spraying this resin over the fiber. So the general process setup is a fiber of 3 layers, stack of 3 layers, with a shape of 30 centimeter by 30 centimeter. And the type of fiber is 450 GSM, or 450 grams per centimeter cubed. And the distance between the nozzle and the fiber stack is about 0.6 meters. And the position is vertical position. Actually, this is the most difficult position in the composite or this fiber reinforced plastic manufacturing process. So just challenging the difficulty will make us the process easy for the other setups. And the viscosity of the unsaturated polyester resin is about 0.3 kg. It's about 10 SAA oil viscosity around that. And we have e-glass fiber, which is a version of chopped strand mat. When we come to the safety modeling or setup for the spray, as you can see it, this is the general modeling setup. We do have a nozzle here at 0, position, and we have the fiber laid here. And we have, as you can see here, we have a cubic shape of flow field. So the resin will be sprayed from this point to this fiber. So this is the flow area. And it is expected to flow 0.02 kilograms per second, the flow rate. It will be sprayed for 10 seconds, and we can get 0.2 kg of resin sprayed within 10 seconds. When we see the ratio between this 30 by 30 centimeter and 3-layer fiber will have a 35 to 65% resin to fiber ratio. When we come to the mesh generation, by the way, before I go to the mesh generation, this is a modeling. Actually, this is CFD modeling, computational fluid dynamics modeling. We are using here a computational method, or we are using just the common practice now. Most challenging equations or challenging relations between parameters are solved, or differential equations are solved computationally, actually using commercial softwares, and in this work I'm using ANSYS software. And when it comes to the mesh generation, as you can see, this rectangular, this cubic flow area is just partitioned or meshed like this. As you can see, there are 1,377 nodes and 1,024 elements. And the mesh was generated based on a medium relevance factor, as commonly done. I applied step by step refining for the mesh. When it comes to the governing the equations applied for this process are actually the model selected is multiphase Eulerian Lagrangian approach, because here the droplets are considered as particles, so they are tracked in a Lagrangian frame of reference, and the fluid or the air is the continuous phase. It is just treated as an Eulerian fluid. So there is a model version in ANSYS software which combines this Eulerian and Lagrangian approach. So the continuous phase, the air and the polyester resin will be the main topics for the analysis. So the solution is this model is solved by tracking a large number of droplets and just tracking each droplet in the flow field. So there will be an interaction between the droplets and the flow field. So there will be a mass momentum in energy exchange between the particle and the fluid. So the process will consider all these things. The CFD package ANSYS Fluent predicts the trajectory of a discrete phase particle or droplet by integrating the force balance on the particle, which is written in a Lagrangian reference frame. It's not Eulerian. For the particle is Lagrangian, but the fluid is Eulerian. The force balance equates the particle inertia with the force acting on the particle. So because this particle has a mass, it has an inertia, and there will be an equilibrium with the force acting on the particle. So this is the general equation applied for this Eulerian Lagrangian approach. This F is additional forces. As you can see that this is a drag force. This UP stands for the particle, and this U is the velocity of air. So this UP minus U minus UP over tau R is the drag force, because when there's an interaction between the flow and the particle, there is a drag force. This drag force is equated by this term. And this is a pressure force. There is also pressure force and also additional forces. These additional forces, in this case, maybe actually these are Safman's lift force. These are due to some microns or Magnus lift force, which are due to rotation. All these things will be considered, but depending on the problem, this F may incorporate different setups. When we come to this tau represents actually the relaxation time for the particle. And actually, this is depends mainly on the viscosity and the drag law applied. Actually, spherical drag law is applied for this setup because the droplet is expected to be spherical. It's not as very fast enough to be a disk, so it's considered as spherical rather than treating as non-spherical. So with this equation, solving this equation in the mesh and the control volume of all the elements, the software will give us the velocity and pressure and also other derived quantities of the process in each control volume or in each element. So based on this analysis and this result, we can discuss all about the results. So actually, for the spray of this relatively viscous fluid, actually we are applying air atomizing nozzles, but there are also hydraulic nozzles which didn't use an air, rather the liquid itself, but air atomizing nozzles are more effective as compared to hydraulic nozzles, because of the air will disintegrate this viscous fluid. So based on that, we applied, it is applied about 4 types of nozzles: a simple cone atomizer, air blast atomizer, pressure fuel atomizer, and effervescent atomizer. These 4 types of atomizers are simulated with this ANSYS software. Only a few of them are capable of atomizing this fluid effectively. That are pressure swirl and a percent atomizer. You can see it in the picture here. As you can see, in the simple cone atomizer is not capable of just spraying. It is a few millimeters. It will no further spray it. When you come to air blast atomizer, as you can see, still it's not effective enough, but this F% atomizer and pressure swirl atomizer results better. Result. As you can see, this is concentration, is cross-sectional view for the concentration of the spray. When we come to, so we can see that from this tests, pressure swirl atomizer and F% atomizer are better with further analysis of process parameters. So we take the pressure swirl atomizer and we did a cross-sectional study of the spray concentration. As you can see in the pressure swirl atomizer, about 10 centimeter distance from the tip of the nozzle to 20 centimeter, 30 centimeter, 40 centimeter, 50 centimeter, and 60 centimeter. So we can see that at 60 centimeter, actually there will not be any resin, polyester resin at all. And if we come to about 0.1 millimeter or 10 centimeter, it is very nice. It looks very nice, but there is a concentration at the center. So we do not want this concentration. Rather, we do want to have uniform distribution. So we do have a better result about 0.3 meter or 30 centimeters. When it comes to the 4 centimeter, it becomes relatively wider. That we need it to be more wider, but also we do want to have uniform concentration. So it's possible to say around 30 centimeter we will have uniform and better coverage. When I come to the conclusion and recommendation, spraying and uniformly distributing resin over a laid-up fiber stack is critical work in the current setup. That means the setup which we are developing. So it has been observed pressure swirl and a percent type of atomizer results a better angle of coverage or area and distance in the simulation. In the case of pressure swirl atomizer, about 30 centimeter distance from the atomizer tip results a wider and relatively uniform distribution. Actually, it is possible to get uniform distribution and better coverage by properly selecting nozzle type, actually, and setting process parameters such as the pressure of the liquid, that means the thermosetting resin, the pressure of the air, and the flow rate. So, with further study of a selected nozzle, it is possible to get a uniform or a better distribution and better coverage of this viscous liquid polyester resin. Okay, thank you for your attendance. Thank you very much.